Hello everyone and welcome to DIANA webinar. My name is Maz and today I have the honor of presenting our landmark release, DIANA 10, and I hope you get some sort of idea about our new development, workflow, and the future direction of development. Just before we get started, I would like to give some sort of technical notes. During the webinar, I'm going to mute your microphones. That's just to avoid the background noise and audio conflict. And after the session, the recorded session will be available either on YouTube or you can basically have access to that and the slides through our shared links. So no worries, the recorded session will be available. So to get it started, I want to have a very short flashback about the history of the company, how we started, how we developed this knowledge, and how we gained the experience to be at the position right now, to be pleased and indeed proud of presenting one of the unique and state-of-the-art solution in the CAE industry. The development of DIANA goes back to early 70s from the main TNO office, Department of Computational Mechanics, and soon after we became commercially available in the Netherlands, in Europe. And by having and developing some successful experience in Europe, we extended our basically market and capabilities towards the Far East Asia in Japan. So over there also there was a good need for performing advanced analysis with specific attention with earthquake and cracking of concrete. So they recognize and acknowledge the capability and capacity of the program. They implemented and used that in their projects. So since then we developed our program, we added more features, capabilities, and in 1998 we acquired FEMSys. It was a British company, and we used their product FEMGV to be integrated in DIANA, and therefore we became, or said we introduced iDIANA in the system of modeling and defining the analysis in the program. So the contribution and activity of our company, TNO DIANA, just keep continuing developing. We had some sort of strategic developments and product developments with big players like Halliburton, with Shell, and indeed developing our market share and recognition of our names in Europe, US, and Asia. And that brought us to the stage to become or start our cooperation with one Korean company, Midas IT, to adapt one of their, at that time, state-of-the-art pre and post and match it and basically define it in terms of working with DIANA solver. So I will talk about the capabilities of iDIANA, about the capabilities of the preprocessor FX from Midas, and advantage, disadvantage, and what we learned from each in the later slides. But having that pre and post integrated, not really integrated, as a part of the semi-coupled approach with DIANA solver, helped us to even expand our market. More and more people tried to use or simulate complex geometries and complex type of analyses with DIANA, which was a good experience for us, and indeed it was a kind of user-friendly factor from the end user point of view to utilize the program. So you can see here more or less every year we had some major release, and then we started, after releasing DIANA 9.4, we started to develop our own pre and post processor, which is fully integrated and at the same time is basically based on the cutting edge technology that we have a full control on development, adapting, customizing, and indeed in the future developing in the direction that we want. We started to do some investigation, developments, and working on that graphical environment. So during those periods also we were active in different markets, and one of the known applications that we had, and we had a very good recognition, was the dam industry or hydropower industry, which based on the specific developments we had with our partners or with our own development team, those features were basically helped us to be recognized as one of the solutions in the hydropower industry, in conjunction with the other features and capabilities that we had for the structural, geotechnical, and oil and gas industry. Another important release that we had was in 2014, when we introduced DIANA 9.5 with changing our old mesh edit to a new look and feel of mesh edit. So that was the starting point of implementing our first development of the integrated environment in conjunction with the solver. One more important activity that we had in 2014, it was opening our engineering office in Arnhem. So this was one of the major and very milestone activity for us, opening office there, in order to be able to provide numerical assistance with the engineering insight to our clients, because this is very important. Most of the engineering applications are based on the design, and these designs mainly need with some sort of simple tools to be done. But by introducing software like DIANA or performing some advanced type of analysis in like finite element analysis, in conjunction with some nonlinear features, we can kind of optimize the design significantly. And how we do that, that's a part of the things that our engineering team can help, assist, and based on the customized discussion and project base, can communicate and develop and share this knowledge to our clients and prospects. So we had other developments in terms of the market in China, in South America, and in 2016, which is right now we are in, I'm proud to announce that in first week of February, we are going to release our landmark product, DIANA 10. The major development here is integration of pre and post-processor. You can generate your model, you can mesh it, set up the analysis, and get the results in one environment, which is all fully integrated in DIANA. So I'm going to talk about all these things quickly, because I think we have a shortage of time. I'm going to also show you the live demo, how it works. So I go through, but at the end of the session, if you have any question, let me know, or we can follow up the discussion by emails, or you can call me, we can have a chat about it. So this was the first interactive environment, iDiana. It was powerful. Still, it is available, but there is no maintenance anymore on that. It had a first set of scripting capabilities, customization of the post-processing, relatively powerful program, had interaction with other programs to import the files. However, the drawback of that was very difficult to set up the complex models. So especially for the new users, this one was not really motivating them to basically dive into simulation of complex models and geometries. So we got this as a feedback and helped us to open discussion and negotiation with Midas IT in Korea. So to develop a customized pre and post processor, which is called FXD, that is the only or dedicated pre and post processor for DIANA program. In return, we also help them to define the kernel for Midas GTS as their geotechnical software. But this is a basically kind of exchange of technology between TNO DIANA BV and Midas IT. So as you can see, the look and feel is a little bit sharper, a little bit modern. At that time, it was very new and state of the art. environment. You could easily generate, visualize, and modify three-dimensional model and feed that to the solver for the analysis. And indeed, it was interactive. However, it had some shortcomings. It was 32 bits. The model or geometry modelers were based on open cascades, so we had the limitation or the restriction in the modification of the geometry. And it was not, the major one, it was not fully integrated. So that means you had to generate your model, mesh it, set up the analysis, and send it to the one intermediate environment, define advanced material properties, do the in detailed setup for the analysis setup, perform the analysis, and get the results back again in FX. So it was not really integrated. However, you can see it was intuitive. You could import many model files from the different programs. It had different mesh engines. We had a huge range of loads and boundary conditions, and they had implemented many good features from the post-processing, very nice and exotic features, animations, clipping, and other stuff, which were at that time very nice and new. So, learning from DIANA, what are the good things that clients shared with us? What are the weak points? And the learning indeed from FX experience from our clients who shared their experience with us gave us more confidence into stepping in our own environment, which is DIANA interactive environment. So as can be seen here, the look and feel is more or less like FX, so it has a very modern look and feel with many icons, control icons. On the left-hand side, we have a multifunctional windows, which is based on the different settings. Either you're at the model level or you're at the mesh level. You have different harmonica windows to see and have access to the mesh sets, to the material properties, to the loads definition, to the support. So everything can be identified and visualized here. And based on the selection that you have, the corresponding segment or sections in the working window gets highlighted. Beneath, we have a properties windows. So based on the selected items from the multifunctional window, you can customize the associated parameters. We have a Python console. This is very important, very powerful. Based on the generic Python language, you can script your model, you can script your analysis, you can script your even analysis procedure from the generation of the model till extracting the results. And you can define some loops to define, basically to go through some sort of sensitivity analysis. So everything can be done in a Python script. Then we have a message window to log all the information as a program goes through the analysis. So you can see all those information in terms of conversions, in terms of some output, in terms of warning, errors. And on the right-hand side, we have two different dialog boxes. The first one is associated to the analysis setup, and the lower one is associated to the output. So based on the selected output, you can select and you can customize and save your output environment. This is very nice feature, very good feature that you can customize that, save it based on your project file, and in the next run or next file, you can basically bring it up and see exactly the same setting. For the current users, maybe this slide could be interesting. In new DIANA environment, our main focus is at geometry. So all the loads, boundaries, settings, all of them are defined at the geometry level. After defining your geometry, you're gonna go for assigning a property. So this assigning property could be in terms of the element type, in terms of interface, in terms of reinforcement, and so on and so forth. After having these assignment done or they taking place, we proceed to the next level, which is generating mesh and then setting up the analysis, performing the analysis, and get the results and check the results. So here you can see in new DIANA, It is very intuitive. There are various display options, advanced selections for the geometry or for the mesh are available. The main geometry engine is the Parasolid one, which is very nice, very important, and very powerful tools that enables you to modify and change the status of your current geometry objects. This is very nice and powerful feature. And indeed, we have an automated and robust geometry check and repair tool, because we are taking benefit of the Parasolid tools, and these things, especially for the auto clash and others, are very important when different segments are interacting and intersecting with each other. From meshing point of view, we have adopted one of the latest technology, including hybrid mesher to generate basically hexahedron and pentahedron and even tetrahedron elements for the model. But this hybrid mesher is a dominant hexahedron mesher. It's very powerful, so you can generate the mesh for any 3D complex geometry with this mesh. Program automatically generates the embedded reinforcement, automatically generates the interface elements for you. You don't need to worry about that. And in terms of the loads and boundary conditions, we have a huge set of loads and boundary conditions are available, which are acting on the geometry. This is, again, I emphasize that all these loads and boundary conditions in DIANA 10 are working and acting on the geometry. Informations are compatible with Excel, so you can use as input, or you can use as an export, or you can use in the post-processing. So as a tabular results, you can see the results in a table format, and that table is compatible with Excel. For post-processing, we have a huge range, not 100% as what you used to have, for instance, in FX, but we do cover more than 80%, and the aim is by end of 2016, we cover the majority of features in the pre and post processor from the FX and iDIANA, plus adding new features that are enhancing your result interpretation, enhancing your model generation, enhancing your analysis setup. So all those new features will be dedicated from us, plus some of the features and functions that you were used to work with that before, and those things will be available by end of 2016. But right now we are in a very good state. We are covering almost more than 80% of the features, so there is no specific shortcomings. From material model and the corresponding classification, we introduce a new set of dialog boxes. Based on the type and class of material, the corresponding inputs gets activated. And moreover, we have a series of aspect selections, aspect icons. So here you can see, based on the type of aspects that you want to consider in your material model, for instance, if it's considered with the heat, if it's considered for the Rayleigh parameters, the associated parameters become active. If you don't check this on, those parameters are off. So this way you work with the optimized or with the minimum material inputs which are associated to that particular analysis. Load combination is another dialog box which is available based on the label of the loads. You can introduce the new load combination before performing the analysis. We have introduced the concept of special and non-special and space functions. This is very important because you can define this spreading or variation of the properties or geometries in basically different dimensions, in 1, 2, or simultaneously on space, or you can introduce a time-dependent or frequency-dependent functions. Property windows, as I mentioned, is basically gives you this flexibility to parameterize your selected items from the drop list. And also analysis windows is another interactive environment that enables you to set up your analysis in a very interactive way. So you can see the operation, you can see the execute block, you can see the different steps. You can double click on each item, the corresponding dialog box gets opened, and you can go through the setting of the options in a very interactive way. And there are many more that I would be more than happy if you could get a chance to try the program. If you have valid maintenance, absolutely you are entitled to get the latest version. Feel free to try it and share your feedback with us. But if you don't have a valid maintenance, maybe this could be a good opportunity for you to look into the features, capabilities, reassess what we offer, and hopefully that could trigger the chance to renew your maintenance with us. So this slide basically gives us the idea how we started, what we learned, and based on the experience that we get from each product, we basically solidify our background in terms of new developments and basically the horizon that we are stepping into to make sure that we are addressing your expectations one step ahead of your request. But that's not the point that we're going to stop. After DIANA 10, our development will continue, especially in terms of the pre and post features, as I mentioned. There will be more interactive file format exchange with DIANA, especially from the building information material BIM formats. We do work on different post-processing features, result interpretation, generation of the report, some application functions or wizard in terms of speeding up your modeling process with minimum requirements or based on the engineering input that are available in the offices to generate your models and perform very good and efficient analysis. From the solver point of view, indeed, that's basically non-stop part from our side. We always work on enhancing the quality of that, speeding up the solvers, covering more options for the multiprocessor, and so on and so forth. Optimizing the nonlinear material models, introducing the new nonlinear features for different material properties. Could be masonry, could be rock, could be concrete or steel, it doesn't matter. We are also focusing on the composite structures. And indeed, our focus will be towards the design checks. So there is a point here, the nature of DIANA is not a design program. So basically, it's not our aim and goal to literally deal with the section optimization or this type of things. What we do is we perform the analysis, and based on the results, we convert those results to some sort of engineering conceptual results that can be interpreted and checked with the reference design codes that you have. For instance, based on the amount of reinforcement, based on the spacing of them, based on the crack that is developing in the model, or based on the reference earthquake model code. So the design check is our goal, not the section design. Fit for purpose application, that's basically the aim, because what we want to do, not only to provide DIANA to high-end analysts and top engineers, we also want to mature the young and the new generation of engineers by doing the daily task, by performing or using DIANA based on the dedicated type of applications. Could be excavations, could be some sort of wizard to create a bridge or making one simple gravity dam. So to give this courage to them that they can easily set up the model, they can easily perform the analysis, they can get the results, and the results are sensible from engineering point of view, with the basic input and parameters that they have in the offices, in the engineering offices, regardless of all the complex inputs, and perform very good analysis in a very short time. So this is the aim by developing some sort of customized fit for purpose applications. So let's talk about modeling concepts. As I mentioned, in DIANA, we have implemented many new features based on the mainly Parasolid tools to able to either import or create your model here, perform some Boolean operations, set up, interact, and move them rotate, extrude. So I quickly go through them to come up with your final geometry. You can import your CAD model, or you can generate your model based on the existing features that we have based on the parasolids. Some of those features are primitive features as a solid, and the others are 2D primitive, and indeed line and point. Having different objects requires to deal with different Boolean operations. So this Boolean operation can be united. You can merge them, you can subtract, you can intersect, or you can move, scale, or rotate your object. So these are very useful features that you can utilize to define your model in different levels. For the selection of the geometry, we do have different selection options. This selection could be as a body, could be as a face, line, or point. So depending on the type of selection that you want to consider, you may choose one of these options and easily select the parts, the body, and the objects that you want from your geometry. Another powerful feature that we have here is automatic clash detection, especially when you're dealing with many intersected and complex geometries. From the geotechnical point of view, with many faults, tunneling, interaction, and intersection with different parts. From engineering part could be, for instance, pile, could be interaction of the foundation. So many things can be considered. What is the important factor here is the program automatically recognizes the different parts that are intersecting with each other and make the compatibility between them to ensure your nodal connectivity later when you mesh it. So this is done automatically, and is one of the biggest advantage in Diana 10. We do have two options. We have a convert body from the solid to sheet. We have conversion from the sheet to solid. So these are the common features that we have. And one of the most important things, again, I emphasize on that, and that's definition of the load and boundary condition. These things are in Diana 10 are defined at the geometry level. So if I have a geometry, I can define a reference curve. Then I imprint the position of this curve, which later we're going to impose some sort of edge load or point load. I imprint them on my reference surface and proceed to the next level, which is loading. So before loading, before defining boundary condition, you should make sure that the bases are, or basically they do have imprint on the main body. Rotate and move of face. This is one of the features that are powerful. So you can have your object and you can rotate, you can modify, you can reshape the geometry based on the rotate and move functionality. You can extract the face, you can extrude the face. These features are available in terms of taking advantage of the existing geometry and extending it to additional parts and corners. We have align face operation. Literally, if you have two or more objects based on the selected geometry points or corners or lines, you can align them with respect to each other. And also, as I mentioned, for special function, you can combine special function based on X, Y, or X, Y, Z based on a space, and you can consider the variation of, for instance, the thickness or eccentricity for the shell if you want to model, for instance, in a very exaggerated shape, one bridge like that. So you can see it here, we have a higher thickness, so we have a higher thickness till it reached to here, we have lower thickness, and again, it goes to the other side. So now our geometry is ready. What is the next? The next is we need to define a property. This property comes based on the dimension of the model and element, based on type of material, based on the type of geometry section, based on the if it is reinforcement or interface, if it is boundary elements, and so on and so forth, that I go through them one by one together. So when you want to assign a property to one geometry, you need to tell to program, okay, I'm dealing with the 2D, 3D, or 1D model, and based on that, what type of elements I'm going to consider and assign to this geometry. Furthermore, you need to assign material property. So as I mentioned in the material property, we have a class that, for instance, you say I'm dealing with the concrete, or I'm dealing with the soil and rock, or I'm dealing with the steel. And based on the class, you have a series of material properties and material types that are available under the corresponding drop list. So by selecting that and selecting or assigning the correct aspects to be included as a parameters, you can set up the parameters, or you may refer to some of the design code input that program already recognize all the assigned parameters internally that we have already implemented in the program. Then for a specific type of elements, you need to assign geometry classes. The geometry classes are assigned, for instance, for the bar, it is associated to the section. For the beam, which is referred to section of the beam, is I, U, or basically angle type, or other type of detailed geometry specification that you may consider for your elements. For reinforcement assignments, we have three different concepts. The first one is smeared three-dimensional reinforcement, which you can tell to the program these reinforcements are smeared in different directions based on a certain percentage per volume. So this is, for instance, 1.5, 2%, 1.5, so you can consider this as a basically factor. Then for the line and face, we have different options for line and face. Especially for the face, it's basically known as a grid concept. So either you can define based on the equivalent thickness, or you can directly define based on the allocated bar size plus the characteristics space. Then program automatically considers how this grid gonna be formed in the model. Or line, width, or tendon, these are basically based on the specific cross section that you can define it in the model. To create or assign property to the interface, we introduce a new workflow or procedure. If you have two blocks which are attached to each other, you only need to select the common face, one face from one geometry, and then tell to the program this face, this common face, gonna be connected, gonna be boundary, or no connection. The difference, if it's connected, it splits, create interface in between, assigns the characteristics properties for that based on the material property selection that you have, and you can have a further control on the number of the integration and other things associated to the that interface. And click OK. Program considers that between these two geometry objects there is an interface. If you're dealing with the symmetry model, and from one side your interface is connected to the model, and from other side it's free, and the free side is, for instance, your asymmetric position, or is this, some sort of supported position, then you can click on support, and in terms of the type of interface, you may select boundary. Program automatically attaches the boundary to the free side. And if you select no connect, then basically it splits two objects with respect to each other, and you have a free zone in between. So two segments are free in terms of movement. I can see there are some questions coming through. Please bear with me. I will get back to you in detail by the end of the session. For boundary elements, for those who were dealing with the thermal or groundwater flow, previously, if you remember, we used to extract some elements from the mesh, and it was very cumbersome procedure, but it's changed. And now what you need to do, you only need to select the boundary of your geometry and tell to the geometry object that this part is subjected to the prescribed temperature, is subjected, for instance, to external temperature or radiation or thermal flux. That's it. The same for the groundwater flow. When we go through the meshing, program automatically generates boundary elements internally, so you don't need to do anything extra with respect to your model. And this is a very important and significant step in terms of speeding up your modeling procedure. For the support, we have standard support allocation based on the standard coordinates X, Y, Z, or based on the user-defined coordinates. which this coordinate could be anything. For instance, here there is a rotation of -45, and the first coordinate, so 1, 2, 3, so the 1 will be in this direction, and I said the second one is based on the Z. So that's how you can define some local coordinate system to your model and assign associated supports to those coordinates, especially if you're dealing with a cylindrical, spherical, or just normal Eulerian one, and then you don't have any problem in assigning them. This is a summary of available loads acting on different bodies, and what is new here, we have hydrostatic pressure that automatically calculates based on the position of the surface that you have in the model. It calculates the column of the water or the fluid and calculates the hydrostatic pressure for you. So you only need to say what is the height with respect to the reference, then program considers from that point, from the reference to the height that you defined, there is a water, and it automatically calculates the triangular or some sort of wedge type of pressure for you. Loading are acting either on the geometry object or based on the geometry edge or imprints. We discussed about that. There are other loads that are needed to be defined to the model. Could be dead weight, equivalent acceleration, centrifugal load, or base acceleration. What is new here is the dead weight. In the basic setup of the model, you define what is the gravity and also the gravity direction. Therefore, when you want to define your self-weight, you only tell to program that I do have dead weight, period. And program automatically considers that based on the reference gravity acceleration and the direction of that, and make sure that you assign the density. It automatically considers the self-weight, calculates the self-weight for you. Furthermore, if you're dealing with some sort of initialization in the model, there are some initial fields that can be introduced to the model. This could be displacement, rotation, velocity, or temperature or heads. Depends on the type of analysis. These things can be assigned based on the original and initial state of the model. Further on, when we assign all these properties, we go for the seeding of the mesh, and we can basically see these assigned seeding. You can set up the type of elements if it is linear or quadratic, using the or selection of our automatic mesher. And based on the selection, you can perform and go through the meshing. Program automatically generates mesh for your body, for your reinforcement, for your interface, and for your boundary elements without any extra steps from your side. So here you can see we have a main column, the foundation, the corresponding piles with the series of interface between them, and also a series of rebars inside these. And program, when it generates the mesh, you can see each mesh set can be named automatically here, and the corresponding reinforcements are generated beneath. So now our mesh also is ready, is in place. The next step is setting up the analysis. Based on the corresponding dialog box, you can introduce a new analysis, then corresponding analysis type, go through the setting of that, and indeed, you can always save these settings based on the DCF, DIANA comment file. So that's one of the most common one that we used to do. You can recall also your old comment files, and also after generating of your model, you can save or export your model based on the DAT file, and you can recall and reload your DAT file even from the old version. So that's also, they're intact. You can still use the DAT and DCF file. Moreover, you can save the whole model as a DIANA project file, DPF, and when you load it in the DIANA, you can directly see all the settings associated to the post-processing, to the settings of your property windows. Everything automatically gets up to date and updated on the screen. So after setting up the analysis, you perform the analysis. You can see all the logging in the message dialog box. You can run the analysis in batch mode. There is no change in that. And also there is a basically results automatically loads in the post-processing for you, or you can load it manually if you're running it separately on the server and you want to bring it on your own computer. You can do that. You can load the results independently. For checking the results, we have different tools available for interpreting the results. I quickly go through them. We have a deformed shape for the basically contour plot in a band format. We have isosurface plot. We have a clipping plane. We have a clipping plot based on the solid view, different angles, different position. We have a threshold value. This is a nice feature, especially if you, for instance, if you're dealing with the concrete, you may say which part is under tension and which part is under compression. And the same can go for the groundwater flow. So which part is wet, which part is dry. You can monitor that easily. We have a gradient view for the contour plot. We have a representation of the interface based on, reinforcement, grid reinforcement based on the contour plot. Vector plot also is available based on this corresponding outputs. So this could be reactions, for instance, or reference direction for the displacement. We have rosettes for the tensor plots, and this is a very nice feature to project them to the outer surface, or you can project them to the cutting plane. This is a very nice feature, especially when you want to see some results which are acting out of certain section, so you can monitor that. For stress strain representation in the cutting plane, the new representation of the crack in DIANA 10 has been changed. Previously it was disk, so that was not the efficient way of presenting the crack. So we came with the new concept, which is very reasonable and basically makes sense in terms of presenting crack by showing a line. These lines are auto-scaled, can be changed in the length, and also can be scaled by color based on the selected output. You can see the same projection on the cutting plane when you have a crack in the cutting plane of the model. The same, you can always use the threshold. And you can get the tabular output in a table format and copy and paste it into Excel for some fancy graphs and preparing the report if you want. For 1D elements, we have a diagram plot, so this could be like a beam type of output. And when we are talking about the layer shell elements or beam based on the different integration points, then you can see the results per corresponding layer or integration. And indeed, a powerful feature that we have, again, I emphasize, is a Python. So you can write and script your own procedure. You can define some sort of parameters. You can define some sort of loop. We have multiple array approach to copy many things. But in this particular case, for instance, we generate one block and we go through some loop to generate all these blocks automatically through the Python command that can be written in a couple of lines in a very concise format. But those are what I set up to now were new in terms of the workflow, in terms of definition of the model, in terms of setting up the analysis and result interpretation. But there are many more. What we have from here, for instance, for the element library, we have a new definition for 2-node class 3 Timoshenko beam to capture the shear failure for the 1D beam. We can assign the layered material properties to the flat shell in DIANA 10. Now it's possible to overcome the locking phenomena that most of the packages encountering if you have some sort of curved face and you have an interface and the orientation of them are changing, then in most of the programs you have locking problems because the normals are interacting and intersecting with each other. But now we have a nice technique to avoid that, and you can have very smooth sliding behavior. And indeed, the matrix reinforcement or smeared reinforcement concept in three-dimensional solid that I gave you some sort of heads up in the previous slide. The new elements that we have defined also is a 5-node pyramid or 13 nodes pyramid that works with the dominant hexahedron measure. So the main domain generates hexahedron elements, and if we hide them, you can see inside, based on the optimization of the model, there are a series of tetrahedron and the pentahedron elements are defined and allocated inside the model, but that comes along with the dominant hexahedron measure. For the matrix reinforcement, as I mentioned, is basically smearing out the reinforcement in the volume of the concrete based on the direction in the X, Y, Z in the reference volume. So you can define that ratio. Then at the material level, we have done significant work to enhance the behavior of modified Mekiava model. And we have implemented and replaced it by the new concept that has been introduced by Professor Mekiava and his colleague, Dr. Fukura. That's for definition of the non-orthogonal cracks for concrete models which are energy-dependent behavior. We have enhanced and updated many features for tension behavior, shear behavior, and compressive behavior of total strain crack model. We introduced new definitions for the soil models to be able to capture cyclic effect in the which are subject to cyclic load. It captures that effect in account. Another very nice and important development and implementation at the material level is our probabilistic material model code, JCSS, and that's very important feature and material models that can introduce heterogeneity in the model to capture very accurate and correct failure compared to our kind of easy assumption as a homogeneous, because when you cast the concrete based on the strength of the concrete from one corner to another corner could be vary. And when you go for the, for instance, creep and shrinkage or loading, the behavior is randomly changing, should be changed. And this is the part, this is the feature that enables you to depict that behavior in your model. And indeed, some material models based on the model codes have been implemented and are available in new DIANA. So in new Mekiava-Fukura model, you are able to model non-orthogonal cracks behavior with the dominant cracking to define the shear strain direction. And also there is an implementation of elastoplastic fracture behavior in the compression zone. And in terms of the input, we made it more even user-friendly, which is input like a total strain crack model. So it's a common input that most of our users are familiar with that. For the shear stiffness curves, we have activated hardening Dronovich, Romberg, Osgood, and based on the input that most of our geotechnical clients get from the shear model or triaxial test, based on that tau gamma shear stress against the shear strain curve that you have, based on that input, you can define that curve into the program, and then DIANA automatically considers that as your reference material model or the ratio of your shear modulus with respect to shear strain. And you can subject your model to some sort of cyclic load. It's a very simple input, but very efficient and effective implementation and material model that you can combine that and assign that to your soil structure type of analysis. For probabilistic analysis or model code that I mentioned to you, basically what model code tells you here that your basic compressive strength can be correlated with other characteristics of your concrete, such as compressive strength, tensile strength, Young modulus, and compressive strain. And based on all those basic correlation, there are some recommendations by code, which basically based on the reference average and standard deviation, it those parameters can be recommended from the code. Program use the log normal distribution to give you some sort of random field of distribution of these parameters in the model as a material properties. The recommendation of this code tells the covariance length is 5 meters. That means within 5 meters material can be changed into properties, and the threshold value is 0.5. But these things can be overruled by user. Having those heterogeneity introduced into the model, and if we have a slab like that which is subjected to the shrinkage, you can see the type of crack that are generating in the model. So it's not all this surface all of a sudden subject to the crack. Based on this random field distribution, you can see one part are weaker, this part is weaker, and the other part are a little bit stronger. So the cracks are happening in the weaker parts. So this is basically the reality of the model that you want to consider to localize the failure in your model by considering the realistic behavior of the material property distribution in the segment or in your model. A special function is also important in conjunction with the material properties because, for instance, in the especially in the geotechnical, your material properties are changing in depth. And this is the function that you can basically assign and correlate with corresponding parameters. Or, for instance, as I mentioned, for random field, having this special function enables you to spread and to define a function to spread the material properties all over the model. Furthermore, we have done further analysis in terms of parallel processing over the element loops, special functions for spreading the results. For the output of the model parameter, this is also a very nice feature that if, for instance, like random field, or if you're doing Young hardening analysis, that some part of the model gets hardened, some part no. It is varying in time and temperature. You can say, I need the output of, for instance, maturity or aging. And these things can be visualized now by contour and see which part is more stronger, or which part, what is the variation of the Young modulus, what is the variation of the tensile strength. All those things can be visualized in the output format. Then we have a new input for frequency in terms of period. We have extension of the logging for eigenmode. And also we have a separate output for reinforcement representing the moment force resulting from these reinforcement. And indeed, we have a dynamic response spectrum input based on the Eurocode and the Dutch-NX that are related to the earthquake and seismic analysis. Quickly, I go through the new and very important development that we have for parallel processing. What we had before was for the solver, and that was for Paradiso and iterative basically solver. Now this parallel processing also is available for eigensolver. And in DIANA 10, literally you can do this parallel processing over the elements to assemble your linear elastic stiffness, to calculate nonlinear stress, strain, and internal forces, and get the final tangent stiffness metrics. So if you have a group of model, program automatically defines certain of blocks with respect to the number of the threads and cores that you define, and it solves and assembles these elastic stiffness for each group separately. So this is very significant and important in terms of enhancing and speeding up the analysis procedure. For instance, in this particular case, you can see if I have something about 250,000 quadratic quadrilateral elements, by increasing the number of the threads, you can see how this going to be reduced in terms of the time for solving this process or assembling this linear stiffness. The same for instance, 52,000 am I right? 5 million elements, tetrahedron elements. You can see how by increasing the number of the thread that reduce the speed of the solution. Same one here for about 100,000 hexadominant elements. So take benefit of this parallel processing, which is available in the normal solver, and try to challenge your engineering with considering more complexity and larger scale in the model. If you remember, for the probabilistic analysis, we have a random field generation which was based on the log normal, but there are other features or other functions can be assigned for this calculation of this distribution. This is a hidden feature, but you can basically consider that based on the covariant method or fast Fourier method or local average subdivision method to consider these random field generation of the material properties. Another, or the last important feature or function or capability that we discussed is how we formulated in terms of the licensing. So in DIANA 10, we are dealing with the new concept for modules. We start with basic, then we go to expert, and there will be more individual components and modules that can be attached to enhance the level of the analysis. So what does that mean? In most of the cases and most of the engineering offices, the basic module is good enough. It has its own integrated pre and post processor with linear features, eigenvalue analysis, some basic nonlinear capabilities, and for the common type of analysis for the universities and the research, those who want to do for training, this is one of the most suitable and indeed affordable module. Later on, if you want to introduce some sort of complexity in the model and analysis. So now you want to have more nonlinear property, more nonlinear capabilities, some more dynamic features, some more complex, for instance, pile or complex reinforcement bond slip type of analysis. Then in that case, you move on to the expert. So expert is the module that is in need for some projects, some applications that are little bit more advanced compared to the daily work. But further to that is the top niche. So now you want to deal with the complex nonlinear cracking, or you want to deal with only geotech, or you want to consider advanced dynamic analysis. In that case, you can add up additional modules to your basic and expert to be able to handle those type of high-end type of projects. The key factor here is everything is add in modules in one environment. So if a user start to learn basic, for expert, it's the same environment. You can load the same model. You only have more features. You only have more capabilities to handle different types of analysis. And when you add more, for instance, capabilities in terms of a structural 1 or a structural 2 or so on and so forth, still it's the same environment. So you don't need to learn another program. You don't need to learn another environment. So everything is basis of one platform, which is DIANA. And that's the key factor and strength of DIANA, that you can use and learn one program, one platform, only add more features and capabilities to be able to handle more complex type of analysis. So that brings me to the end of this presentation. I would like to go through one quick example together, just to break all these slide concept. So I open DIANA. This is the look and feel of that. When you click on New, the first dialog box that you see here, it tells you what type of analysis you want to do, what's the name of the project, where do you want to store it. So all those information can be set up and assigned here. I say I want to define a box girder. And this gets stored in my documents. The type of analysis is just a structure. The dimension is 3-dimensional, so you can optimize your input and setup based on the selection of the dimension of the analysis here. The reference basically model size, the type of elements, and the reference measure that you want to consider for this model. So I click OK, and my working environment gets ready. So here, the left-hand side is a command box for the basically Python. So as I go through the setup of my analysis, you can see all those things are reflected in a Python script here. Here is my message box, and on the left hand side on a multi-window functional window, if I go to the reference system, you can see my units. We have a dynamic unit system. You can easily change at different units that you want, if you want. And we have definitions. If you remember, I was talking about the gravity acceleration, the reference gravity direction, the fluid density. If you want to consider some sort of Rayleigh damping parameters to your model as overall, you can define them here. In this particular case, I'm gonna change to Y just for sake of illustration. And let's set up the model. I'm gonna draw one section representing my main body of the box girder. You can have these input by clicking on adding a sheet, by defining X, Y, Z coordinates of individual points, or you can easily copy and paste of those information from the Excel or from the reference, basically the data that you had. If I click OK, you can see this is my reference shape of my box. I'm going to define another section inside and subtract them from each other. So once again, I go to create sheet, and in the second phase, again, I select these reference coordinates that I defined before, click on OK. You can see this is my new shape, and it's done. So if I go to the geometry under the shape, I have two reference shapes associated to these two shapes that I defined. The next operation is subtract. I go here, the target face is my main body, and the tool is my inner part. You can do many operations here. You can subtract, you can unite, but at this moment we want to subtract. You can click on preview how it looks like and click OK. So this is literally what I want from my model. I hide my grid for a second. So this is the reference 2D cross section that I want at this moment. Now I want to extrude this to generate a solid model. So for that, I have an icon here representing the extrude option. So here, if I select my reference sheet, I can easily use my reference coordinates, drag them, and you can see nicely they are extruded in the space that I'm working with. So in this particular case, I don't do anything except extruding it 10 meters with respect to the current position. So this is my reference, basically solid box girder, which the global direction is Y. So now you see why I changed the gravity direction in Y, because I want to see my gravity goes down in the direction of Y. This is just for illustration. So this is my box. The next step is to define some sort of tendons on the top flange. So what I do here, I'm gonna hide my solid sheet and the solid body, and now I define my line. So starting point, I have some data that I can reuse them. 2.85 and 0. This is starting point, and the ending point is minus 4.5, 2.85, and 10 to come and cover the full range of my solid box. If I show the solid box, you can see here is starting and end point of that. The next step is to have some sort of basically copying this, because now I have this line here. I want to copy 6 times to cover all these tendons on the top. We have a multi-array copy, so I'm gonna select this. Relative displacement with respect to the current one in the direction of the X is 1.5 meters, and I excuse me, I need it 6 times. Click OK. This is what you see here as my final model, including my tendons positioned in the right direction. So what else do I need is the bearing position or the support position. To this end, I'm gonna basically go to the create sheet, and I define one rectangle representing the position of my bearing. I click OK. So here you can see whatever I do, it generates here and simultaneously reflects in a Python script based on the corresponding Python syntax here. So the next step for this is to copy this sheet, put it here, and in a multi-array move these two on top. So what I'm gonna do, I click on basically, maybe it's better I directly go with the copy. The direction is minus 3.6. So you can see immediately what is appearing here. Click OK. So everything is all right. Now I'm gonna copy these two and move them up here in the direction of Z, which is 8.5 meter with respect to original place. So if you remember, I said if you want to define your position of the load or boundary condition, you need to always use imprint function to imprint the position of them on your model. So if I hide them, you see no trace and effect of them on the model. So I activate them and go through the imprint operation. So what I'm gonna do, I'm gonna imprint face, select the reference face is the bottom face, and the tools are these 4 faces that I have. Direction. The direction is in the Y direction, so in the gravity direction. So I change that to 0 and this one 1. Click OK. And now you see those reference plates after imprinting eliminated, and you see the position and imprint of them on the main body. So if you remember in the presentation, I said after defining your geometry, you need to assign the property. Let's do that together. I'm gonna go for assigning property. I select the main body, the type of element is structural element, the type of material property. I go for just a concrete, linear elastic. So let's start with the basic input. I can define this concrete. My reference Young modulus, well, could be 2.4, E10, 0. This, and the corresponding density is 2.4 E3. So that's all we need for the solid. There is no need for geometry data or data information. Click OK. So you can see here in the reference all those information reflected, what are the material properties, how we assign and define them to the geometry. The next one is our bars, or basically tendons. We go to the property definition for reinforcement. For simplicity, I hide the box. Let's select all of them. You can see all the lines are selected, automatically gets highlighted. I add a new material properties, linear elasticity. I call this tendon. Click OK. What we need as a material properties is only Young modulus, 1.96. And since they are rebars, they are supposed to be embedded elements. What we need to do, we need to define the corresponding geometry section. So what is the cross section of these? So for this particular case, I define something like 0.001 and click. So before I click OK, look, all these lines at this moment recognize under the normal shape. As soon as I accept here, in terms of the assignment of the reinforcement property, they are automatically recognized as a reinforcement. You can see all of them are transferred to the reinforcement group. So we have generated the model, we imprinted the boundary conditions, we set up the material properties. The next part is to define a support for our model. I show the model. You can attach support to the model. So I call it boundary conditions as a name. I select the faces associated to the bearings, and in translational direction I define constraint. You can see them. Then the next step is assigning some sort of loading. Let's start with the global load. Defining the global load, self-weight, click OK, dead weight. Then I have a pressure load. And this, we're going to assign it to the top face. And distributed force. What would be the value? Minus 2E4 in the direction is important, in the direction of Y, global Y. You can see that. And then we define pre-stress to our solids. So if I once again go to the load, pre-stress, solid. Now we have basically reinforcement bar pre-stress. I can select them and define the corresponding load for my pre-stress. So everything has been assigned in terms of the different loads, different setups that we had. And what we need to do now, we need to go through the meshing. I define seeding. Maybe I cancel my selection. Okay, I select the body. The element size, for instance, 1.5. Go for the hexa model. If I click preview, you can see how the division, this is element size gonna work. This is a big one, maybe a little bit smaller, so you can always take benefit of the preview. Click OK. We are ready to basically define the mesh. So it takes a few seconds to generate the mesh for you. It's a hexa mesher. Perfect. So now if I go to the mesh tab, you can see all the mesh sets which is a one body, and these are the embedded one that are highlighting as I hover my mouse over them. Under the load, we can define a new basically load combination. At this moment, we have one for self-weight, one for pre-stress, one for pressure. I can add one considering the effect of each with the factor of 1. Close. So everything is done here. The next is to set up the analysis. I perform just simple linear elastic analysis just for illustration, structural analysis. For instance, if you want to do any setting, you can just double click, corresponding dialog box opens, and you do all the settings. If you want to customize your output, you can just open that and you can customize that. What I want to highlight here, still you can get your output based on iDiana, based on FX, or based on the current Diana. The default is current Diana, but you can still get your output based on the other or the old products that we used to provide. So if I click on Run, so here you see some log information going through the analysis. The analysis done. So here, based on the load combination that we had, for instance, load combination 1, if I go for the output, let me adjust it, for the nodal results, total strain, deform, undeform, and with mesh or without mesh. So you can see this is only with self-weight, this is a top pressure, this is the pre-stress load, and the last one is the combination of all of them. So based on this selection, you can go to the output selection, go for instance to the contour. You can introduce new cutting plane. So in a real time, you can cut your model. This could be based on the reverse view at any angle, any rotation, or you may kind of make this as a slice. So then in the slice format, you can cut your model at any angle, any rotation that you want, and you can go through this variation in the model. So one more thing that I would like to highlight, you can basically export or save your model based on the DAT file. So if I say, okay, Diana in desktop output, I can go to my desktop output and I see my box girder. The same DAT file that you used to work is available. The whole model information, everything is available in a DAT, in a text format with all the material properties. And the same goes for the DCF. So if I right click here, save, and this can go again to the basically, for instance, my desktop output, for instance, MAS DCF. So if I open this MAS DCF, here you can see all the settings are reflected. Here you can modify that and load it back again into the analysis setup, or you can directly import your basically that file. Beside of that, all these information are logged. You can import your DAT file as well. All this information, as you go through the process, are logged in a kind of Python script in your Diana user, in your C user, in Diana IE folder. So if I open this file, you can see whatever we have done. We created the model, we called that box girder, we defined the hexagonal model, the reference sections, how we went through, we extruded 10 meter, we defined the first tendon, so everything has been reflected here in detail. So it's up to you. For instance, if I copy everything up to defining the mesh, just for sake of illustration. So you can see it's nicely and quickly generates everything up to the point of defining seeds. So now, for instance, you can change this section. You can change and regenerate everything automatically. Now, instead of 0.5, 0.15 now, for instance, I go for, what was that? Maybe 0.5. Preview. So now I have, if I mesh it, I have a bit coarser mesh. So take benefit of this Python scripting for replaying, redefining your model, changing your geometry, updating your model, only one part, one segment, one table with the corresponding part, and that way you can certainly speed up your modeling and indeed going through the sensitivity analysis much more efficient than before. So hope with this live demo you get some information about the new concepts and workflow we define in Diana 10. I'm available if there is any questions. Please let me know. I would be more than happy to share and discuss with you. As I mentioned, the recorded session will be available either by link. You can reply to my GoToWebinar invitation, or we can share the link on YouTube so you can easily refer to our YouTube channel and follow not only these other dedicated recorded sessions with Diana and our technical sessions and other things from our YouTube channels. So I would like to thank you all for paying attention and hope you all enjoyed this presentation. I'm available to have some sort of discussion about your questions.